Hello, my name is Darren and I'm a visiting researcher at Microsoft. I'm also the founder and director of a research centre called CAMERA, which is a UK-based visual computing and AI research centre with a strong focus on working with industry, including healthcare, entertainment and sport. One technology we use extensively at CAMERA is motion capture, and we use motion capture to work extensively with digital characters. CAMERA has around 20 academics involved and around 40 PhDs and postdocs, and we collaborate with over 20 companies on projects across entertainment, healthcare and sport. So today I'm not going to talk about my work at Microsoft, maybe that one will be for the future. Instead, I want to broadly talk about digital characters for mixed reality, what gaps I think there are, and where I think AI can help. I will also touch on some work we have done in this area at CAMERA and other people's work in the area, but I want to focus if I can on opportunities in this area for growth and collaboration. So this is the homepage of our research centre. We have two studios, one in Bath, which has 100 square metres, and a 600 square metre studio in Bristol. We do motion capture for research and industry. We can even capture a tennis court in our Bristol studio as the space is so large. The image on the screen actually shows the Imaginarium Studios in Ealing, which is Andy Serkis's motion capture studio, where we worked on multiple projects related to motion capture rigging and animation. I just wanted to also give some acknowledgements to some collaborators on the projects I will touch on today, some of who are currently members of CAMERA, some of whom have now left, and others are external academics. And one of the satisfying things about working at a university, of course, is that when people do eventually leave, they hopefully go on to great places. So just to give you some context again, my last PhDs have ended up at ILM, Digital Domain, and Apple, working primarily on motion capture and animation projects. Okay, so why digital characters for virtual experiences? One reason is that avatars give us a way of connecting socially, or for work over remote distances, or to enjoy experiences, shared experiences in the metaverse. For example, like in Altspace, or in the real world in the future using Microsoft Mesh, where the representations might also be entirely different from one another. Another application is for autonomous virtual beings. We might want to interact with an entirely AI-driven avatar for training, as a guide, or entertainment. For example, like Mika, the avatar by Magic Leap, or think back to Project Natal by Microsoft when the Microsoft Kinect launched, or characters in video games such as Red Dead Redemption 2. The diversity of applications for avatars is truly vast. Looking at some of our work in this area, here are two experiences we worked on with Satori Studios, the BBC and Aardman, both of which won awards at international festivals, such as Cannes and Raindance. So both of these required creating digital versions of an actor, suitable for animation of their face and body, motion capturing them with a production team and then animating them. In both cases, the pipelines are, with some exceptions, mirrors of what you would expect in a modern video game or visual effects studio, barring perhaps the quality or volume that you can produce, and you can only produce with a large team over a period of time. So given that these pipelines reflect modern industry, I wanted to talk a little bit about this first before focusing on where AI opportunities lie. Also, I wanted to say that my focus here is on avatars across the scale of realism. So from not very realistic to human realistic. And unless the avatar is heavily stylized or abstract, the following steps for avatar creation and animation will broadly apply. In terms of faces, here are a set of tools we developed while working with the Imaginarium. We have a generic blend shape rig with around 140 blend shapes for different expressions. Given a 3D scan of a person, we combine non-rigid iterative closest point methods with deformation transfer to put these shapes onto a new identity. Then, given a facial performance represented as motion capture, say 2D or 3D points, we solve an optimization problem to find the best set of blend shape weights to describe the input signal, and this creates the facial performance. We can see the pipeline represented in the diagram on the top left here, where iterative closest point and deformation transfer create new blend shape models. As an added extra bonus, we also developed an approach where we can take image information between the markers and feed this into the optimizer. For example, if we see a wrinkle on the skin, we can make sure that a shape with that particular feature is triggered in the blend shape model by the optimizer. To create and animate the body, we typically first use photogrammetry to acquire 3D meshes. Again, we use a non-rigid approach to fit a generic rig to the scan, but this time the rig is a bone-based skeletal rig. And we correct the joint positions if necessary and incorporate extra geometric detail from the scan if desired. For body animation, the skeleton acquired from the motion capture system has to be retargeted onto the body skeleton. The facial rig and its performance from the head-mounted system are also added to the body to create the final face and body animation. As I said, this pipeline is a good proxy for a standard industrial pipeline, but of course variations exist. And third-party tools like Faceware, Mixamo and Wrap3D are often used in-house as part of a production process. And by iterating at each step, the desired final quality can be reached. Reflecting on this pipeline for creating production-ready assets, which would make great characters for virtual experiences, a few things are obvious in terms of AI opportunities and where AI can fit. The first is at the character creation stage. That is, we would like to have automatic generation of models and automatic rigging solutions so that they are ready for animation. This implies that the rigging method can handle edge cases as well as common cases. And above all, quality should also be high. There should be no geometry or texture artifacts at all. The second AI opportunity is in the animation. Capturing performances and setting up controls between the captured performance and the animation rig is still a hassle. Even with the best tools available, high quality is only achievable with hours of offline work. In terms of the virtual character scenario, there clearly are gaps to address with this approach. Looking at the bigger picture, if our goal is to cross the uncanny valley, then visual effects might be taken as the bar for how far we have come. This is because the process is offline and therefore can be hand corrected, painted and rendered with our latest expensive techniques. However, while we might be able to create the illusion of a real human for a fleeting moment, often lost on a second viewing, I don't believe we really know yet how to bottle up and deliver human realism. In this case, there is clearly an opportunity for AI, in addition to the fact that the production process still requires hundreds of hours of work. Video game or real-time characters have different requirements in visual effects, and the disadvantage that mistakes cannot be fixed offline. In recent years, the best real-time digital humans are also still the result of hours of work creating high-quality assets and then setting up bespoke performance-driven animation pipelines tailored to the performer. This is still generally the case today, and while exciting recent tools like MetaHumans look like they will help us close this gap and may be useful for virtual experiences, challenges clearly still remain. For example, the highest quality assets are still heavy and difficult to personalize. A great deal of work is therefore still required to connect them in a useful way to mixed reality experiences. On the research side, we now see the emergence of deep neural networks trained, for example, from libraries of 3D scans that automatically create animatable models from single input photographs or scans. Here we also see gaps. On the one hand, video game and visual effects assets require detailed clothing and hair, as well as realistic skin and rigs with often complex control layers. On the other hand, the parts of research that are useful have to be productized. It is also important that the method is reliable and doesn't produce unexpected errors. It can't work on just a few cases, but might have to work reliably for many cases the original authors didn't account for. But that is not to say that academic work in this area in recent years has been nothing short of amazing. and constantly inspires advancement in high-tech areas. There are clearly years of research ahead of us, and a huge landscape of problems for us as a community to focus on. Looking at some of our own research, let's go back to digitizing and animating characters, but this time animals, which we have been using not just for AI research, but also for developing mixed reality experiences on HoloLens as part of exhibits at various creative festivals. In order to make asset creation easier, we applied our human body pipeline, including photogrammetry, rigging, and motion capture, to dogs. The data was used to create a parametric rigged model where you could vary dog breed and also create animation. However, one application of the model is also to train markerless motion capture systems, which we did using Microsoft Kinect as an input. The approach captures not only skeletal motion, but also estimates the animal shape, and also gives interesting results on other animals. The model can also be used with the MOSH algorithm, typically applied to humans using Simple. Using MOSH, sparse motion capture markers can be used to estimate animal shape and skeletons directly. Moving on to faces, we considered different ways to create animations quickly and intuitively. Firstly, we wanted to be able to generate keyframed animations that produce not only realistic transitions, but the option to add subtle variations and differences each time you animated the same keyframe sequence. One application of this is the fast generation of background characters in video games, for example, for crowds. In this case, you want multiple avatars reacting to the same event, but for each animation to be subtly different. Secondly, we wanted to explore ways to allow anyone, even totally inexperienced users, to author sophisticated facial expressions. To achieve this, we created an authoring tool based on genetic algorithms. At each iteration, users are presented with a range of example faces and select the closest match to the facial expression they are visualizing in their mind. As iterations progress, the system converges on the user's ideal expression match. As well as empowering creatives, the tool has also been used in psychological and clinical studies. For example, we have already been using it as a way to study how different populations, for example, people with different psychiatric conditions, perceive faces. In this case, we find that different groups cluster expressions in different parts of the facial manifold. Moving forward, I think this also shows another real benefit of avatar technology, including the tools we use to create them. They offer a lens to learn more about ourselves and how we perceive the world. Of course, we might also want to interact with the real world while in an immersive experience. For this reason, we've been studying interactions between ourselves and real-world objects while in VR. We've been learning to track rigid and deformable objects in real time for these experiences and modeling interactions between our virtual hands and virtual representations of these objects. Wrapping up the talk, I wanted to go back to the motivations for creating digital characters for virtual environments. I think this is the most exciting time there has been for avatar research, especially with the growth of mixed reality and products such as Microsoft Mesh. And most exciting of all is that we haven't even scratched the surface of what's to come. Thank you for listening and enjoy the rest of the workshop.